Finally, on our program, we have Pete Swan. He's going to be speaking about dual space architecture.
What we're going to do is talk about a strategy that we've come up with. It turns out that we started way back when in NASA time in 98. That was so last century, guys. Anyway, they came up with the answer that we could do a space elevator in 100 years or so. And then Brad Edwards got a little upset and he said, no, we can do it now. So he came up with the answer we could do a space elevator as soon as we get the material. And now we have multiple materials that should work. Now we have a lot of work to do, and I'm not downplaying the importance of the material, but we feel like we should start and get going on building a space elevator. Well, in parallel, we have to address all the risks that Eduardo and Kevin talked about earlier. And one of the risks that I want to point out and emphasize to everybody is we cannot piss off, so to speak, the rocket community. They are a big brother, and we want them to ask us to join in an approach to the future. So we want them to do what they're very, very good at, which is they're operational today. That's good. We won't be operational until 2036 or so, somewhere around in there, pick a number. But we want them to keep doing what they're doing and initiate the dreams of many, initiate the movement to the moon, initiate the movement to Mars, initiate the space solar power constellation. Make sure that rockets continue to do what people are dreaming of and what they have visions of. What we propose is that we come in and then do the heavy lifting. Now, people on the space elevator, I have always believed that that will happen in time, but we are building the first generation, which is robotics. And what we can do for humanity is move mass, a lot of mass, and we can do it in a green manner. So what we've come up with is the terminology dual space access architecture. And I think that's important that we recognize that we want to be partners with rockets. Now, it turns out we have an image on the left there that was done by an intern that we had last summer. And she started understanding what I was talking about. She was my intern. I was working with her. She was in Scotland and I was in Phoenix. And she started understanding it. Now, she just graduated as an astrophysicist or a physics major. And so she kind of mentioned along the way that she was an artist also, and would I, accept a little piece of art in her paper? And I said, sure. And she nailed it. She nailed it. She's got the space elevator in parallel with rockets, and that's the message I want to pass. That's where we want to go. We want to join the rockets in this adventure toward the future. We want to help humanity move off planet, and we want to engage in programs like space solar power, where we can help stop or slow down global warming significantly. So we need to help. The dreams are there. Mr. Bezos is there. Mr. Musk is there. NASA wants to put uh, people on the moon, and they want to use a big rocket to do it. We've got people dreaming about Mars. We've got people dreaming about sending payloads to all kinds of planets and even interstellar. And we can move the big mass and do it in a green manner. So what we want to do is join these dreams. So when you talk to Mr. Musk or his representatives about going to Mars, 1,000,000 metric tons. Oh, say that again. 1,000,000 metric tons is what he's advertising. I calculated that was 50,000 launches. His approach is to go to Mars with his Starship, but what he doesn't mention too often is each mission Starship that goes to Mars requires 5 launches. You got to refuel it, you got to put people up there, you got to supply it and everything else. And then it leaves low Earth orbit and goes to Mars, but it's 5 stinking launches. That's why he's talking about 1,000 launches a year. I mean, he's really out there. The National Space Society has grown from the L5 Society and another one, American Rocket, but it turns out their vision is still the same. Let's put people productively working in space. And so Gerald K. O'Neill had a class in Princeton where they designed these vehicles, 4 miles long, a mile in diameter, or something like that, rotating cylinder at the L5 location. But nobody asks the question, how much mass? How about 10,500,000 tons? So then there's a lunar village. A lot of people are getting on this. And this is really a remarkable statement that Europe and America are going to the moon. And of course, if you go to the moon, you ought to have a little village. Of course, there's going to be a Chinese village right next to it. So, the point is we're going there. So we're thinking 500,000 tons to there. And then, of course, John Mankin's activities where they want to do, can you guys see my slides? I hope you can. I got a strange little note. Somebody say yes.
Can see your
Okay,
slides.
thank you. Okay, then John Mankins has this belief that he can stop global warming, or at least significantly slow it down. And he needs 5 million tons. Now, we've recalculated that. It's only like 3 million tons to do his constellation, but it's still a lot. And so you can see that the dreams are out there for many, and they want to do this. This is occurring across the globe. And here's a whole bunch of calculations on other missions that we talked about in 2013. And so the bottom line is the reference missions we're talking about is a bunch of mass to GEO and beyond. And quite frankly, they can't do it with rockets. The impact of delivering 0.5% of the mass on the pad to the surface of Mars is really a silly concept. FedEx wouldn't make any money doing that. So what we want to do is we want to jump in the 2036 time period and provide the avenue for moving heavy mass. If you compare what's been done in the past, and I took this estimate, and it took me about 2 weeks to do this, but it came out there about 22,000 tons is all we've put into orbit since humanity started this race. And it turns out most of that's into low Earth orbit. So they've even been graciously given twice as much mass that they compared to GEO. And then if you look on the lower right, that's what we believe we can do with 6 space elevators distributed around the globe in 3 galactic harbors. Now, they're either going to be one big corporation that's making a lot of money, a lot of value, or it's going to be 3 competitors. But it's something like that. And the characteristics we've all talked about, I'm not going to spend the time on there, but we need to start talking permanent space access infrastructure. As discussed by Eduardo and Kevin earlier, infrastructure is what we're talking about. And of course, the report, if you haven't read this, I highly recommend it. Jerry did a very good job on this one. We have 2 aspects of the Green Road. One is we raise everything with electricity. The second is we enable missions at GEO that will impact the environment, like space solar power. Just 1 or 2 quick charts just to reinvigorate the thinking about rockets. Apollo 11, I can't say enough about that. I love that. It was right at my prime time when I was going to grad school, and man, it was awesome. Anyway, they delivered 0.5% to the surface of the moon of the mass on the pad, and they didn't reuse anything. So, that was really good. It was 0.2% got back to the surface of the ocean. So if you can put the perspective of let's start a colony on moon, but we only deliver 0.5% of the mass that we put on the Earth's launch pads, you're talking about a silly proposition. Now, it's the only thing you can do today. So let's have rockets do it. But we've got to remember that the conundrum of rockets is their delivery statistics are really stinky. Now, that's a technical term, okay? Delivery statistics are poopy. Anyway, here's some numbers I did. They're all lousy. Delivery to GEO and delivery to geosynchronous transfer orbit, basically the same as going to the moon. And that's bad. Space solar power, holy schnookers. a lot of mass. And if you do that at 2% to geo, that's a bad, bad case. So here's a quick chart that David Dotson did, which was really good, showing the energy requirements by 2050, when we also have to have the Paris Accords met and get rid of nuclear and coal and all that kind of stuff. So we need to meet this number by 2050. And so the answer is space solar power, in my mind. 2 gigawatts of power from each one, and you have to do it at 9,000 tons. Now, that's being discussed right now. It looks like it's like 7,000 tons, but our report showed 9. So that's basically it. But that's like a bunch of launches. Now, what we did is, or I should say David did, is he came up with a chart like this. The red line is very simple. That's 1,000 launches a year, we estimated SpaceX, delivering 20 metric tons to orbit each launch, to GEO, each launch. The purple one is space elevators being implemented in about 2035 and getting up to speed by 2045 or so. And then we start lifting the heavy mass. So we can match the needs of the globe out here by 2065 or so. And so, you know, it's really amazing what we can do when we lift heavy mass for the energy requirements of the Earth. Now, just to put it in perspective, the needs are going to be phenomenal for electrical power on the surface. This is what we can do. So we say, okay, we're going to do a portion of this. So that needs like that much tons to GEO, and there are that many launches per Starship. And the Starship is huge. It's as big as a Saturn V. 138 years for rockets to do that. Those are estimate numbers. Don't you know, depend on them, but those are just estimates. So the answer is a permanent space infrastructure. And that's really what Kevin and Eduardo were talking about in the economic trades and the value. And this is a chart from John Mankins, which is prototype deliveries to low Earth orbit and to then on up to GEO. So he's going to be able to start his constellation by the time we start. But we're here to start delivering that 3 million tons to GEO. Whereas these are prototype vehicles to show that space solar power satellites work. And so we're really in the time of need for space solar power. We can actually support them tremendously. So bottom line is dual space access. Basic message is we should do the heavy lifting, and we're going to do it with a green manner. And the value is so great for this type of stuff. So why space elevators? It's no longer why space elevators could be cheaper. It's because we must do space elevators. The dreams of so many are out there. We need to support them. So we must do space elevators. So our team in ISIC is really valuable. We want to encourage and support and jump into this. The real kicker is space elevators avoid the rocket equation. And nobody mentions that in the big discussions about space. That's the key. We avoid it.
Thanks, Pete. Really appreciate how we can work with rockets. I think it's a great presentation. Thank you so much.